Chapter 5, number 48. The figure shows the normal force N experienced by a rider of weight W, which is given as mg, as it always is, on a Ferris wheel as a function of time. A. At what time, A, B, or C, or D, is the rider accelerating upward? And what is the magnitude of the maximum acceleration experienced by the rider? So we need to basically do a free body diagram for our rider. So this is the person riding, and that person is held in place or is moved by the normal force, which they called here N. I'm not a fan of that. I like forces to be called F something, but we'll go with what they say. And likewise, we have the weight pulling the person back down. They call that W. Not a fan of that either, but we can stick with that, right? The universe doesn't care what symbols we use. And together, these two things produce an acceleration. So before we even get into any kind of formal thing, we can even look at this and say, in the case where the normal is more than the weight, so that we have some weight pulling us downward, but we have a much larger normal force, when we add them, and the purple here will the purple will represent the net force, it points upward, and the acceleration is always in the same direction. So in that case, we get an acceleration which is upward. In the other case that you can imagine, where the normal is less than the weight, then we get the same thing for gravity, so the same, roughly same guy, but now the normal is smaller than that, which means the net force points downward, and the acceleration, which is always in the direction of the net force, also points downward. So we really can answer our questions without actually computing anything or even formally using Newton's laws, although we are definitely using them. So our question is, at what time A, B, C, or D is the rider accelerating upward? So we need the normal force to be bigger than the weight, which means it must be bigger than 1 mg. And our scale is in terms of mg. So basically, accelerations upward are going to happen whenever we're above the 1 line. So anywhere over here, or clearly when at point A. They didn't ask this, but you say, what else is going on? At point D, the person is accelerating downward because the normal force is under the weight, and so the object falls a little bit, the person falls a little bit, but not as much as in free fall. And at B and C, where the normal equals the weight, then we find that at that moment there's no net acceleration. All right, and then part B, what is the magnitude of the maximum acceleration experienced by the rider? Well, that clearly occurs at A, and now we are going to have to do a little bit of the formalism. We're going to have to say, well, from our diagram, the net force is N minus W, and from the second law, the net force is M times A. This will be maximized when the net force is maximized. So we say, in that case, actually in every case, we can say together that the normal minus the weight is M times A, which tells us that the A is the normal minus the weight over M. And if we say here, well, our maximum A will happen when the maximum normal subtracts the weight and divide by M. Our maximum normal is 1.21 or 1.20 times mg. Sorry, written very badly, sorry. Is 1.20 mg minus, well, the weight is just 1 mg, and then we're dividing by m. So our maximum is 0.20 mg over m, or 0.20 g. So our maximum acceleration is 2/10 of the free fall constant. If you need the number to confirm for yourself, that is 1.96 meters per second square. And that would be the maximum acceleration the person would ever suffer upward.